Do we have a
I know you're checking out the school, and
Take a quiz.
you better not be checking out the grades.
So there's gonna be no chapter 9 test. Chapter 9's material will also be covered in the chapter 10 test, because there's kind of no way to do the chapter 10 content without the chapter 9. So we did the chapter 9 quiz as a take home. We'll have a 10 quiz and we'll have a 10 test that also has, we'll cover the same aspects.
Okay.
So before we get started, I want to talk about a boo-boo that I had made. So I just discovered here recently that the way I set up our grade book was wrong. That I had assigned the 50% weight to the final exam and the 15% weight to the test grades when they should be flippy-flopped. So I just made that update here this morning. So if you see an abrupt unexplained change in score, that's what happened. Hi. Thank you.
No.
What was it? So just to give you guys fair warning, that's what happened. I did that this morning, so. Anyway, questions about that? My apologies, was not, obviously I don't intend to make mistakes, but like, stuff happens, I'll own that. If you want to talk about it more, I'm happy to have that discussion. Today, we're going to be starting chapter 10. So in chapter 9, basically what we did was we learned what a derivative was and how to find a derivative. In chapter 10, we're going to look at applications, like what can I use this new derivative, idea of a derivative to do, and then like what's the procedure for doing that. Now, we've kind of hinted at these ideas already in chapter 9 because I know where we're going, so trying to provide a little bit of context. I've already kind of hinted at these ideas. So the first thing that we're going to talk about in chapter 10 is going to be finding extrema, so finding maximums and minimums. And we're going to talk about doing that algebraically. So if you remember, there were two types of maximums and there's two types of minimum, right? There's local, which is like a local maximum is the highest point in like some open interval. And the same thing for local minimum, it's like the lowest point in some local or some open interval. And then there's absolute or global maxima and minima. So a absolute maximum is the highest point across all points in the function. Now, since it has to be over the entire function, is there always an absolute maximum minimum for a function? No. Like if I have arrows going up and down at both ends of my graph, there is no absolute maximum or minimum, because there's always another higher point because you can go to infinity, right? So we're going to talk about how to find these, and the technique differs just slightly. So let's start with locals. So there are two techniques we can use to find a local maximum or minimum. We have what's called a first derivative test. We have a second derivative test. So the way we start is for first derivative test, we're going to look for where the first derivative changes from positive to negative or negative to positive. So a minimum if I have a negative derivative, that means the function had a negative slope. If it changes to, if the derivative then changes to positive, it means the function then would have a positive slope. So if I go from negative slope to positive slope, that's going to be a minimum, right? And then obviously if I'm going from positive slope, positive derivative, to negative slope, negative derivative, that means I'm going to have a maximum. What will the value of the derivative be if it changes from negative to positive? Would be 0, right? Assuming that the function is, assuming the derivative is continuous. The second derivative test says I have a local minimum if the first derivative is 0 and the second derivative is positive. So that would be like concave up, which would make sense, right? Concave up would look like this. So that would be a minimum. Or I have a local maximum if the first derivative is 0 and the second derivative is negative. Or is the second derivative negative is concave down. So concave down looks like this, which looks like a maximum. Is everybody okay with this idea? So again, the details of these first and second derivative tests would not be given to you on a quiz or test. That's something you'd have to remember about, like, what do I need to look at and what does the result mean? Okay, so that's something you are going to be responsible for, making sure you know that. So far, so good? Okay. So this is all about local mins and maxes. To find an absolute maximum or minimum, we're only going to do that if we have a closed interval. What's the difference between an open and closed interval? Do you guys know what I mean when I say open or closed? Closed interval has the brackets at the ends. The open interval has parentheses at the end. That's all we're talking about. Is that okay? So on a closed interval, little spelling error there. Closed interval. What we're going to do, you can do a first or second derivative test, identify the local extrema. And then we need to check our local maximums and the endpoints to see which one is the biggest. That would be the absolute. And we check our local minima with the endpoint and the endpoints, see which one is the smallest. That would be the absolute minimum. Okay, so we're still identifying our locals the exact same way that we would. Then we just need to check, is that local min or max an absolute min or max? Is that local? Yeah, anyway. Does everybody feel okay here? Now, why do we have to check the endpoints also? So say like our function looked like this. Because we're on a closed interval, the endpoints of our graph are points. So I have a local min here, I have a local min max here, but this guy's my absolute max, and this guy, my absolute minimum, right? That if you have a closed interval, the endpoint could be the highest or lowest point. You have to check that in addition to the locals. Does that make sense as to why we have to check the endpoints here? Only if you have a closed interval, though. All right. Let's do some examples. So it says find the coordinates of the local maximum or minimum of the function, and then identify them as maximum or minimum. So the first thing that I'm going to want to do is I'm going to, actually we'll do this both ways. We'll do it as a first derivative test and a second derivative test, just so you guys get a feel for the difference. Majority of the situations you guys will run into, you could do it either way. It'd be a question of preference, and more often than not. For either method, though, the first thing I'm going to want to do is to take the derivative of our function. So our function is 2x squared minus 12x plus 15. What's the derivative of 2x squared minus 12x plus 15? Guys just turned in a quiz that should have gotten good at this over the weekend. The fact you're not all beating down my doors to yell the answer. Brooklyn, what do you got here? You're mouthing answers. Just take a risk, dude. It's okay.
4x.
That much is good. Yes. Keep going.
Minus 3.
Not 3. What's the derivative of 12x?
0. No, wait.
Derivative of 15 is 0.
Yeah.
So that's good.
Isn't it just negative 12?
Yes!
Oh.
Wonderful. You got it. Everybody's okay here? That's it. 4x minus 12. So far, so good? Everybody happy? You remember doing this? This should be fast and easy to do these, right? All right. What I'm going to do now is I need to find what are called the critical points. So the critical points are going to be where the first derivative is equal to 0 or where it's undefined. Now in this class, if you're doing the derivative yourself, there aren't any places where the derivative is going to be undefined that were not part of the domain already. No, that's a lie. There might be one situation you can think of. But here, is there any place where I plug in x and I don't get a number that comes out of this? 4x minus 12?
Yeah. Well, it would be 0.
But that's just negative 12 then, right?
Yeah.
Is there any value I can plug in for x that a y doesn't come out of this? No, why? Why is that the case? How do you know? Right away, just by looking at it. What type of function is this? It's a polynomial, right?
Yeah.
The domain of a polynomial is always all real numbers. So is there any place where a polynomial is undefined? No. There's none of those. Is everybody okay with that? More often than not, that's the case, but you should at least give it a moment to check, right? If the derivative is just a polynomial, there's nothing to check. And we should be specific here. We're checking if the derivative is undefined at a location where the function itself is defined. So if I had like a 1 over x here, I take the derivative, it's still going to be undefined at 0, but it doesn't matter because it was already undefined in the function. All right, and then we'll solve 4x minus 12 equal to 0. What do we get? 3, right? Okay, so if I'm going to do this now as a first derivative test, I'm going to make a sign diagram. My critical points are going to be on my x-axis. So in this case, I have only one critical point, it's just x equals 3. I'm going to pick a value for x that is less than 3 and a value for x that's greater than 3. And then I'm going to plug those test values into the derivative and just look to see if they're negative or positive. I don't care what the number is. You can find the number if you want. You don't need it. All you need is the sign. So if I plug 2 in,
2 is negative.
I get a negative. And if I plug 4 in, I get a positive. Since my derivative changes from negative, so negative slope, to positive, what type of extrema do I have? If we're going from decreasing to increasing, it's a minimum. Very good. So then to find the coordinate of this, because that's what the question actually asks for, I'm going to find the y value now by plugging that into the original 2x squared minus 12x plus 15.
So you plug 3 into that?
Yes. So that's going to be 18 minus 36 plus 15, I think, is negative 3. Does everybody feel okay?
Yep.
All right. If I did this as a second derivative test, okay? So they're both accomplishing the same thing, okay? No difference in the output. The process is the only difference.
Doesn't matter, like on tests, you won't ask, like, use a first derivative test or stuff to us.
No,
Okay.
you're free to choose. So for the second derivative test, I've done all this stuff already, right? The stuff above has been done, but I need the second derivative. That's the first thing I'm going to do. What's the derivative of 4x minus 12?
It's your 4.
4. That's it. Yep. You got it. Okay. Then what I'm going to do is I'm going to take my critical values, I only have one of them, and plug it into the second derivative. There's no x in there, so just the output is 4, right? Since that's positive, I know I have a local minimum. I don't have to do a sign diagram here. All I care about is the sign. I think the second derivative test is usually the easier of the two, but it depends on how difficult is that next derivative to take, right? If the next derivative is difficult, maybe the second derivative test is easier. It's just a question of like, you know, like, what do you feel more comfortable with? And then we do the same thing. To find the y coordinate, we just then take that 3 and plug it back in to the original function. And we get the same conclusion. So again, first and second derivative test do the same thing. The start of them is the same. The only difference is like, how do I tell if it's a minimum or maximum? That process that you use to tell what is it is different. That's it. Next example. Okay. So this question asks to find the x coordinates rather than the coordinates in general, right? It doesn't ask for an ordered pair here, just the x's of all the local maxima and minima for the function yada, 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 and then identify them as maximum or minimum. Okay? How do I start?
You find the derivative of that function.
I find the derivative of that function. What's the derivative of x cubed minus 4x squared minus 3x plus 12?
3x squared,
Yes.
minus 4x.
Close.
Oh, minus 8x.
Yes.
Minus 8x, minus 3
Yes.
plus 0.
And again, you could write the plus 0. It's not wrong to do that. I'm not going to. We don't need to do it. It just kind of evaporates.
Mm-hmm.
Everybody happy?
Yes.
Okay. Then we set the derivative equal to 0 and undefined. And I'm going to save myself some writing. I'm going to do this. Is there anywhere where the derivative is undefined? No. How do you know?
Polynomial.
It's a polynomial, right? Yeah. So no critical values from that. And again, that's more often than not the case, right? The majority, vast majority of situations you'll deal with in this class, that'll be the case. But we should make mention, some of us will take a real, like a full calculus course at some point in their career. It's nice to have like seen the full rule, not just like the streamlined version that you're gonna need in here. All right. So then let's worry about 3x squared minus 8x minus 3 equal to 0. What type of an equation are we solving for here?
Starts with a cube.
Quadratic. What are the different ways we have to solve a quadratic equation?
Quadratic formula,
Quadratic.
factoring.
Great. Quadratic formula, factoring, and graphing. If I'm on the IB exam, which one would I choose?
Quadratic formula, probably.
Or maybe even just graph it.
Oh,
Because it's a time situation, time matters. Now, we're gonna use the quadratic formula here because, but the IB will not care if you have an answer rounded 3 decimal places, right? Or 3 sig figs, like they're totally cool with that. Like no reason to grind through this, but let's do it because it's also like a math class and it's a little more rigorous to do it this way. And I love rigor, So again, I'm just applying the quadratic formula, negative b plus or minus square root b squared minus 4ac all over 2a. If you haven't got that memorized by now, God help you, you probably never will. But we've used it, I don't know, for 4 years now. All right. So we have 64 plus 36 is 100. The square root of 100 is 10. So 8 minus 10 is negative 2. Divided by 6 is negative 1/3. And 8 plus 10 is 18. Divided by 6 is 3. Is everybody happy here?
Yes.
Feel comfortable on what we did? Hopefully all of my mental math is right. You never know. Okay. So if I did this as a first derivative test, I could draw my sign diagram, put my critical points on my sign diagram, pick test values in the intervals in between those critical points. So one to the left of negative 1/3, one test value between negative 1/3 and 3, one bigger than 3. And then we'll plug those into the derivative, and I don't care about the number that comes out. All I really care about is the sign, right? So if I plug -1, I have 3 plus 8 minus 3. It's positive. If I plug 0 in, I have 0, 0, minus 3. If I plug 4 in, I have 48, minus 32, minus 3. So, because we're going from positive to negative, what is happening at -1/3? Mm-hmm. And because we're going from negative to positive, what's happening at 3? Local min, right? So that's my answer. So, again, this question doesn't ask for the coordinate, it just asks for the x values. So I don't have to do any more. Again, just to get a feel, so you guys can build some intuition, decide which method you like better. We'll also do this as a second derivative test. Sound good?
Yep.
Okay. First step in that is I need the second derivative. Oh yeah.
6x minus 8.
Okay. So again, we just took the derivative of this guy. So that's the 6x minus 8. And then I just compute. So that's going to be -2 minus 8 is -10. That's less than 0, so that's a max. And we do the same thing for 3, so that's 18 minus 8. That's positive 10. So that's greater than 0, that's a min. What do you guys think? Again, first or second derivative test, in this case, I would say 6 of one, half dozen the other, right? There's not much difference in terms of like how easy that was, because the derivative here was a little bit more complicated to deal with than last time, but like, come on, Mr. Kulik, it's not bad. You're right. Okay. Next one, it says, given h of t equals 4t cubed plus 3t squared minus 6t, on the domain -3/2t is less than or equal to t less than or equal to 2. Find the coordinates of all local extrema, and then classify them as maxima or minima, okay? And then write down the coordinates of the absolute maximum and absolute minimum. Okay. So this piece here, we just need for part B. Doesn't affect us at all for part A. We're going to ignore it till part B. Is okay? Okay. So if we're looking for extrema, first step is to
Get the derivative.
find the derivative. What do we got? 4t cubed plus 3t squared minus 6t.
Is it 12? That 12t squared plus 6t minus 6.
Wonderful. Everybody happy? Cool. Then we'll take that derivative and find the critical values. Is this derivative ever undefined?
No.
No. How do you know? It's a polynomial, right? It's cool. Like, Is it always this easy? I mean, a lot of times it isn't easy. All right, we'll set this guy equal to 0. Now, I noticed something right away to make this problem a little bit easier. What do you notice about this?
6 moles.
Yeah, everything is divisible by 6, so if we just divide both sides by 6, that makes life like a lot easier. And we can probably factor this just by inspection without having to do the long factoring, right? Since it's either +1 or -1. In these two spots, we just have to kind of sort it out. Because this second, or the middle piece is positive, I know I need a +2t and a -1t. So I do that. So those are my two critical values. Now I should do one thing, I guess, before I move on, just for safety's sake. I was given a domain here, right? I would just want to take a minute and check to make sure both of these answers are in the domain that I'm given, which they are, right? They're both between -1.5 and 2, so I wouldn't expect it to have been otherwise, but like, they could get tricky on me, you never know. Or I could have made like a catastrophic mistake, and sometimes it's worth just like checking. All right, so if I do this as a first derivative test, make a number line, have my critical values. Now here I have to be a little bit careful because I need to make sure the t's that I'm picking are inside the domain. So I don't want to pick -2 here. -2 is not my domain. And I'm going to do something atypical here. Normally I'd pick like a 1 in this spot. I'm not going to do that. I'm going to pick 2 because I know I have part B coming where I have to check the endpoints. So I'm going to do that here. And unlike the previous problems, I am actually going to find the answer to these because I'm going to use that answer in part B. So like as long as I'm doing this work, like I might as well do it now rather than redoing it later. So if I plug in -1.5, I'm going to have -3 minus 1, that's -4, times -0.5, so that's +2. I don't care about the value for 0. So I have -1 times +1. Well, that's negative. I don't care that what the number actually is. You could write it down. It's not wrong to do that. If I plug 2 in, I'm going to have 4 minus 1, that's 3. And then 2 plus 1, that's 3. 3 times 3 is 9. Yes, sir. Everybody okay with what I did? Notice that I did actually compute these numbers this time because I'm going to use those in part B. Everybody ready to go?
Yeah.
All right. So, -1, we're going from positive derivative to negative derivative. That's a maximum. And here we're going from negative derivative to positive derivative. That's a minimum. So we've done that, right? What did the question? Did it ask for, oh, that wants the coordinates. I wasn't done yet. Sorry.
Wait, so when you're doing a second derivative test, do you plug the x values into the original function or is it into the derivative?
We'll do the second derivative test in a second.
Okay.
You can see. But just hold on that
Yeah.
just for a second. Is that okay? Yeah, I forgot what this function looked like. What is it? It's 4, 3, 6. I think the signs, did I do that right? Nope, I have them flipped. So that's 4, plus 3 is 7, plus 6 is 13. All right, so let's see, that is 1/2 times 3/4 minus 3/2. So that's going to be negative 5/2. No, 7/2. Fourths. Yeep. I think. Assuming I arithmetic that correctly, which I think I did. Oh, it's early though, guys, you know. Who's ready for fraction mental math at 8 o'clock in the morning? 8:30. Okay. So part B. What I do then in part B is I'm going to just compare 3 things. Oh, why? I didn't need to do that at all. All right. So I need to compare f of negative 3/2, f of negative 1, which we already did, f of 1/2, which we already did, and then f of 2. Okay, so this is going to be like oops. All right, so what do we got here? Negative 27/2, yuck. And then I have 27/4. And then I have plus 9. So that's going to be 54/4 plus 27/4 plus 36/4. So that's going to be negative 9/4. No, positive 9/4. All right, that's 50, yeah. And then if I do the same thing for 2,
I have 32 plus 12, that's 44. Oh, minus 12 is 32. So what I want to do now is I want to look at these values. Which one is the biggest? Between 9 over 4, 13, negative 7 over 4, and 32.
32.
32. So what that tells me is that my absolute maximum is at 2 comma 32. Notice that was not one of our local, that was not our local maximum. That's okay. Which one is the smallest?
Negative 7 over 4.
Okay, so that tells me this is our absolute minimum is at 1/2 comma negative 7 over 4. Which was a local minimum. That's okay. Give me both. So the only thing that changed from part A to part B, I took my two answers from part A, also calculated the coordinates of the endpoints, and just compared the y's, right? I just had looked at the y's to see which one had the biggest y, that's the absolute maximum. Which one has the smallest y, that's the absolute minimum. That's it. Is everybody okay? If I did this as a second derivative test, I'll calculate my second derivative, which would be,
24t.
oops, this guy was h, I guess. 24t plus 6, excellent. And I still have that, so just compute for 1/2, and I get
Now, what do you plug in that to?
second derivative.
Oh, okay.
So 12 plus 6, that's 18. Since that's greater than 0, I know this is a local min. Plug into -1, that's going to be -18. So that's a local max. Then we need to find those coordinates. We'll do it the same way we did there. I'm just going to borrow that work. Is everybody okay?
Yeah.
All right. And 18.
Yeah, and of course you just plug that y, the x into that original function, right?
Yes. The original function is always going to give us the coordinate. The y coordinate, I should say. So there's part A. For part B, then, I just need to look at h of -3 over 2, and then h of 2, which I'm going to just steal the work from over there. And then that one is 9 over 4, we said. So we have Alex, what's up? You okay? Is that okay, guys? Again, it's like 6 of one, half dozen of the other, whichever one you feel more comfortable with. Walking your way through. You're getting the same results. I think it's more or less the same amount of work. This one looked like less work because I borrowed all the calculation from the other one, so I didn't write down as much stuff because it had the answer plugged in from the other side. But you know, it's like whatever you feel more comfortable with seeing your way through. The vast majority of the problems you'll be given, you can do either. And I think I have just one more example, and we'll call this quits for today. Sound okay?
Yeah.
Okay. This one says, a toy rocket is launched upwards into the air. Its vertical position, s meters above the ground at t seconds, is given by s of t equals yada, yada, yada. Find the average velocity over the time interval from t equals 1 second to t equals 2 seconds. Okay. Average velocity. What is, when I hear average, what do we think? Should think slope. So I'm just going to do s of 2 minus s of 1 over 2 minus 1. S of 2 is going to be negative 20 plus 36, so that's negative, negative 20 plus 36 is positive 16, plus 1 more is 17. Are you okay there? Part B says to find the instantaneous velocity at t equals 1 second. When I see instantaneous, I think derivative. So I just need s prime of 1. Well, let's start by calculating s prime in general. What's the derivative of negative 5t squared plus 18t plus 1? Negative 10t plus 18? Yes, that would be the answer. So when I plug 1 into that, I get 8 meters per second. Part C says to find the maximum height reached by the rocket and the time at which that maximum height occurs. So that's when I'm asked for a maximum or minimum, I'm really going to be looking for our extrema. I'm going to do a first or second derivative test here. So I'm going to take that first derivative that we already calculated above in part B and set it equal to 0 and undefined. Now I know that there's no values that make it undefined because that first derivative is a polynomial. And when I add 19 and divide by, subtract 18 and then divide by negative 10, I get 5 over 9, and I guess that's seconds. Now I should confirm that that is actually where the maximum occurs. I'm going to make a choice here and do a second derivative test on this because my first derivative is linear, which means that when I take the second derivative, it's a constant. So there's my maximum, occurs at 9.5 or 9/5 of a second, or what is that, like 1.4 seconds, I guess. It also asks me for the maximum height. To get that, I'm just going to do S of 9/5. So what was the thing again? -5t squared plus 18t plus 1. So what's this going to be? -81 plus 162 over 5 plus 1. So times 5 is -405 plus this ain't right. What's going on here, Mr. Kulik? What happened here? Did I screw some?
81 over 5.
Well, oh yeah, because I still have a 5. Thank you. Brilliant, yes. Yeah, I canceled too many. That makes a heck of a lot more sense. Okay. Thank you. So that's 86 over 5. So we'd say the rocket reaches a max height of 86 over 5, or if we probably want to divide that. What is that, like 21.2? No, that's not right.
17.2.
Thank you. Meters at t equals 1.4 seconds. Something like that would be our answer. And again, on a problem like this, I turned everything into decimals rather than fractions because, like, this is a real world problem. Nobody's gonna be like, that rocket went 86/5 of meter, 86/5 meters. And they're gonna be like, no, nobody would say that. What do you guys think? Is that okay?
Yeah.
So more or less, this is just like a continuation from chapter 9, right? We're still just using all of our derivative rules, and we're just now doing like an application. So you guys should be able to do on, oh boy, that's a long way down. Oh, there's another one still. I'm done with it though. Are you guys over it?
Yeah.
I think I'm over it too. 334 to 336, numbers 1 through 15.
And when is this due?
Sunday at midnight?
Along with the 9.394.
Yeah.
That's on my water.
Yes.
Thank you.